Hi, I'm Alexis Harold, and I'll be introducing our noise canceling and audio amplification device project. Our project focuses on developing a stationary noise canceling and audio amplification system that works with any standard wired headphones. The main idea behind this design is to provide the benefits of active noise cancellation and improved audio quality without requiring an expensive headset. The scope of our project was to build a desk-based ANC and amplification system that prioritizes sound fidelity, power delivery, and overall performance. Since the device wasn't meant to be portable, we were hoping to focus on higher quality processing and amplification components. Our objectives centered around a few key goals: achieving low to mid frequency noise cancellation, delivering clean audio amplification, maintaining universal compatibility, and implementing real-time DSP-based ANC with low latency performance. We wanted all of the subsystems to integrate seamlessly into a single complete signal chain. In terms of value, our system is designed as an affordable alternative to premium marketable headsets currently. It's external, so users can keep their current wired headset and still gain noise cancellation and improved clarity. It's built for stationary environments, places where people are focused on work or study, and it actively suppresses the noise background while amplifying the desired audio. The goal is to improve concentration and improve productivity without the cost or limitations of integrated ANC headsets, because those are not the most accessible for companies or school systems to use in shared workspaces. To achieve this, the system incorporates several important hardware and software features. Hardware-wise, we used a Daisy Seed microcontroller and a Class AB amplifier. We wanted to use a dual microphone configuration and in a 3.5 millimeter jack because that's headphone standard. We implemented low noise power regulation for consistent audio performance. On the DSP side, we combined feed forward and feedback algorithms, adjustable gain control, a low latency filtering pipeline, and UART-based debugging for visualization and diagnostics. The design emphasizes modularity and reliability. Because it's stationary, we could prioritize high performance over battery life, and the modular structure makes testing, debugging, and future expansion easier. Overall, the project demonstrates a functional proof of concept for external ANC and audio amplification and highlights the potential and challenges of delivering without the cost of integrated headphone systems.
Hi, my name is Landon Lamakusa, and I'm going to be going over the design of our analog audio amplifier. And pictured here is our LT Spice schematic of the amplifier, and you can see that we have three stages or three chains. We have a gain stage, a voltage buffer stage, and a Class AB or push-pull output stage. And while we might have been able to get away with just using a single op amp to amplify our signal, we wanted to optimize the ability to drive resistive loads. And so we added the voltage buffer and Class AB output stage. And as you can see, it's a stereo amplifier, so we have a path for the left headphone signal and right headphone signal. Moving on to simulation results, we targeted a bandwidth of around 200 kilohertz, and as you can see, we had 260 kilohertz, and we targeted a phase margin of around 60 degrees, and we got 64.6 degrees. The gain was as expected at around 5 volts per volt. Following this, we started to design a PCB board, in which Cole will go into further details about, but I want to first discuss the results, the test results of our PCB board that we received. And this is the output waveform of a 1 kilohertz 2.5 volt peak-to-peak input sine wave, which is what we use for our simulation as well. And you can see that the waveform looks clean, or the gain is around what we simulated for. So it's about 4.84 volts per volt, which is very good. And one issue that we found with our physical PCB is that the bandwidth is much lower than what was expected and designed for. And so we have a dominant pole that is at an unexpectedly low frequency, around 3 or 4 kilohertz. And as you would expect, this would mean that at low frequency, our audio sounds really good. And at higher frequency, you start to hear some distortion. And so with more time and further investigation, we'd be able to figure out what is causing this pole, whether it's something with our PCB design or the design itself. But now Cole is going to go over the design of the PCB.
Hello, my name is Cole Nesius. I'm part of Team 10 with the noise canceling and audio amplification device. And today I'm here to talk to you more about the PCB layout and design. So we have 4 dedicated layers, 2 to the ground, 1 to power, and 1 for the components in the top layer. The 2 ground layers are actually tied together. They make one continuous ground layer, and that ensures that we have a clean, stable grounding across the board. Component placement is very important because unlike the schematic, when you're doing the layout, you have to worry about the routing and the distribution of the parts. So for compact routing, we minimize trace length and crosstalk between analog and digital paths. We added copper cores, proper mounting plans for heat dissipation, and isolated high current DC-DC converter region for sensitive amplifier stage. Here is the schematic of our design in Altium. Here you can see the two paths of the right and left clearly there through the dual op amp, and then feeding out towards the output jack. This is our PCB final design. Here you can see how we have proper clearance between our power. So power is on the left. That goes from our screw terminals from where batteries get connected to the DC-DC converter. All the capacitors hug nice and tight to that DC-DC converter for minimum trace length, with vias that go straight down to the ground nodes from those capacitors. And then on the audio side, on the right side, that's where the signals go through. You can also see the capacitors and resistors also hug nice and tight to the components, and there is clear separation between power and audio. And this is our 3D design.
Hello, I'm John Michael, and I'm going to be talking about some of the noise canceling algorithm theory and some of the hardware we have going on. So, for our noise canceling algorithm, we are using a filter X least mean squares algorithm, which is the industry standard that's used in noise canceling headphones. So what this algorithm does, it produces a filter W that creates an anti-noise signal, and this anti-noise signal destructively interferes with any ambient noise that's going on around you. So the inputs for this algorithm is a reference mic, which is a microphone that's outside of the ear cup of the headphone that picks up any ambient noise around you, an error mic inside of the ear cup so we can monitor the performance of the algorithm and update the filter W, and of course the music source, any of the signal you want to be hearing through your headphones. And then the outputs of the algorithm is the anti-noise signal and then the music. So for the hardware we're going to be using a Daisy Seed digital signal processor with an ARM Cortex M7 and a 24-bit codec at 48 kilohertz. That is important if you want to have high fidelity audio. Then for our reference and error microphones, we're going to be using electret microphones, so analog, and then a summing amplifier to combine the anti-noise signal, the DSP outputs, and the music source. So here's kind of a representation of what the algorithm is doing. So the first thing we want to do is estimate the secondary path. So in the bottom right there, you'll see what the secondary path is. So it goes from the DAC or the source, laptop, phone, whatever that you're getting your music from, and that is going to go into the amplifier, into your headphones, into the error mic, then back into your laptop. So we want to know how this path is going to be affecting the signal you're hearing, so we know how that signal is being affected in our algorithm. So once we have the secondary path estimated, we freeze and we go into this loop. So first, the reference mic captures ambient noise, and then that ambient noise is used to calculate the filter W, and the inverse of that noise is outputted. So the destructive interference is outputted. Then the error microphone captures the disturbance, so basically which is what's going on inside of the ear cup. And then using that information from the error microphone, the LMS algorithm is updated, or W is updated. And that just keeps on going forever and ever until you want to take off your headphones.
Hi, my name is Jorge, and I'm with Team 10, and I'm going to go over more of the DSP and digital side of things. For the digital portion of the project, we originally tried to implement the full filtered X LMS algorithm directly into the Daisy Seed in C++, but ultimately we ran into several limitations. The secondary path estimation and the FX LMS update rule are both mathematically heavy and pretty difficult to implement in real time on an embedded processor. On top of that, the low-cost electric microphones we used introduced poor audio coupling, and the combined system delay from the mics, ADC, DSP, DAC, and amplifier caused a lot of phase errors. Once the phase shifts too far, the cancellation signal can actually become constructive instead of destructive. Because of these challenges, we pivoted to validating our ANC algorithm in MATLAB using higher quality microphones. This let us isolate the DSP portion and test the concept without the hardware limitations. The results are shown here. The estimated secondary path impulse response confirms that the system was able to accurately learn the physical path from the output to the error mic. In the PSD plot, you can see the clear reduction in noise energy, especially at low frequencies where ANC is most effective. The RMS plot shows the same thing over time. Once ANC activates, the error mic noise level drops significantly and stays lower throughout the test. These results validate the algorithm and show that our ANC approach works. To wrap up, we successfully built a stationary noise canceling and audio amplification system that works with any standard headphones. We demonstrated real amplification and confirmed ANC feasibility through MATLAB testing, even though full real-time cancellation wasn't achievable with our hardware. Our main takeaway is that the wide spectrum ANC requires more advanced DSP resources and higher quality microphones. But our design establishes a strong proof of concept and a solid foundation for future improvement. This was Team 10's presentation. Thank you very much.